Hello everyone, I am Siddharthan. Currently, we are in the seventh module of our hands-on machine learning course, and this seventh module is all about building machine learning models from scratch. In my previous video, I have explained you what is the intuition behind a support vector machine classifier, and in today's video, let's try to understand what is the mathematical basis of a support vector machine classifier. Okay, so let's get started. I'll just give you a quick recap of what we have discussed in the previous video. So we know that a support vector machine or a SVM model can be used in both classification as well as regression tasks, but it is mainly used in classification problems, but that too in binary classification problems. So binary classification in the sense the model will try to classify the data into two groups. So you can see the two groups here. So one type of data is represented as blue colored circles and the other type of data is represented as red colored squares. And now we are going to use a support vector machine classifier in order to classify these data points. So what does a SVM classifier tries to do is it will try to draw a hyperplane that can separate these two data points. Okay, so you can see this black color line. So this line is called as hyperplane. So even though this is a line, let's call this as hyperplane. I'll explain you why we do that. But for now, remember that it will try to draw this hyperplane which is represented as this black colored line. So this line will separate these two data points. And now we have other important term called as support vectors. So support vectors are the data sets or they are the data points present in a data set which lie closer to this hyperplane. So you can see these three red colored squares, right? So these three data points lies closer to this hyperplane, hence we call them as support vectors. Okay, and you can also see these two blue colored circles, so they also lie closer to this hyperplane, and hence we call this as support vectors as well. So it is not the rule that there should be one support vector, so that's not the case. So you can have multiple support vectors in a data set, so you can remember that. And then we have something called as margin. So this margin is the distance between the line that is drawn from the support vector. So if you draw a dotted line that joins all the support vectors from one side and another dotted line that can join the support vectors from the other side, so if you measure this distance, and this particular distance is called as the margin, and your hyperplane lies exactly in the middle of this margin. Okay, so this is how we will try to draw this hyperplane. So we will try to find the support vectors and we will try to find this margin and we will try to draw this hyperplane in this middle part. And now the one thing you need to remember is that this margin should be as far as possible. So this margin distance should be greater so that our SPM model can make good predictions. So the reason we are creating this margin is to have some tolerance value, or to have a cushion to make predictions. So if we have just this hyperplane alone, then our model cannot make good predictions because some data points may overlap. But if you have this tolerance, if you have this margin, let's say that there is a data point which lies in this space. So let's say that we have a new data points and we try to plot this data point, and it lies at this point. Now the SVM model can see that it lies in this part of this margin, and then it will try to classify this data point as one of those red colored squares. Okay, and if you have another data point which lies in this space, it can try to classify this data points as one of the blue colored circles. So this is how this margin works. So we need this margin should be as long as possible, so the distance should be greater so that we can have a good cushion or a good tolerance value. Okay, and now if you have a new data set, and let's try to plot this new data set. Let's say that this green colored square is the new data set, and if we try to plot this, it comes in this place. So we can see this visually and say that this is one of the type of this red colored squares, right? Because it lies in this part of the hyperplane. If another data point lies in this space, we can call this, let's say that there is a new data point which lies in this space. So in this case, we can say that this particular data point is one of the blue color data points. Just a second. So we can say that this data points belongs to one of those data points, and this data point belong to these red color squares, right? So this is how we can visually say that SVM can classify the data points. But now we need to understand how a SVM classifier can mathematically determine this. How it can look at this data point and say that it is belong to this kind of data. So that's what we are going to deal with in this particular video. And you can see that this is a linearly separable data set. So that's what I have mentioned here. So which means this data set can be separated by a straight line, right? But in real world, there are a lot of data set which cannot be separated by a straight line. In that case, what we will do is let's consider this example. Let's say that we have two features, x1 and x2, and in this data set we are trying to draw a SVM classifier. So no matter what, you cannot draw a straight line that can separate this red colored triangle and blue colored circles, right? So these are the two data points you have, and you cannot use a straight line to separate them. In that case, what we can do is, if we have a third feature, in that case we will try to plot this data points in a three-dimensional space, and in that case we can separate these two data points using a plane. So you can see this plane here, which is represented as a gray colored space. So this is how you can build a support vector machine classifier by increasing the dimensionality. So in this case you have only two features, and because of that you are not clearly, you are not able to clearly separate the data points. But in this case, as the dimensions is more, we can clearly separate the data points. And in some cases we don't have the higher feature, so we cannot have more dimensions. So in that case what we will do is, so if a data set has a minimum dimensions, minimum features, we will try to use some mathematical functions called as kernels. So these kernels are the mathematical functions that will try to increase the dimensional space. So this smaller dimensional space can be converted into a larger dimensional space. So this two-dimensional space can be converted into a three-dimensional space, and so on. So once you do that, you can easily classify the data points using some plane. So if you have a two-dimensional space like this, so it is just a two-dimensional space, right? So it just have x-axis and y-axis. So in that case, so I'll just draw x-axis and y-axis. Let's say that we have y-axis here and the x-axis here. So this is a two-dimensional space, and if you have a two-dimensional space, you can easily draw a straight line which can separate the data points. But if it is a three-dimensional space, we need to draw a plane. If it is four dimensions or five dimensions, we have to use a hyperplane. Okay, so that's what is called as a hyperplane, a plane which is in multiple dimensions. So hence we generally call this line as a hyperplane. Okay, so I hope you understand why we call this as a hyperplane, because we basically use it in a multiple dimension in most of the cases. So, and for this we use something called as kernel, which are mathematical functions to increase the dimensionality, right? So I hope everyone is clear up to this point. And now we are going to see how a SVM model can determine a new data set. If you take a new data point, which data groups does it belong? So we are going to discuss that. So let's say that we have two features, x1 and x2, and we are trying to plot the data points in these two features in a graph. Okay, and let's say that we have 2 points. So the first point is represented as p1, which is in red color, minus 3 comma 0. So this is the coordinate of this point. So x1 is the, so this minus 3 is the x1 coordinate and 0 is the x2 coordinate. Okay, so it's just like x and y axis. So and then we have the second point as p2, which is represented as this green colored dot, which is the coordinate of this p2 is 3 comma 3. Okay, so we have this two data points, and now we are going to draw a hyperplane which can separate these two points. So as this is a two-dimensional space, we can just use a straight line, and we know that the equation of a straight line is y is equal to mx plus c, right? And now we are going to see how a hyperplane or how a line can separate these data points. So let's say that the slope of this line is -1. So let's take this blue color line, which will act as our hyperplane for our support vector machine classifier. And let's say that the slope of this line is -1, and the intercept of this line is c is equal to 0. So we know that the equation of the line is y is equal to mx plus c, and m is the slope and c is the intercept, right? So slope is nothing but it basically tells you what is the orientation of your line is. So if you have a line like this, so let's say that we have a line like this, so this line would have a slope of +1. So a slope of +1 basically means if x1, so let's join these points. Okay, so let's join these points. So slope of 1 plus 1 represents if x1 increases by 1 unit, then x2 also increases by 1 unit. So if you have a line which is in this particular direction, it would have a positive slope. Okay, but if you have sorry, just a second. So in other case, if you have a line like this, so line like this blue color line, which is in the opposite direction to what we have seen before, so this kind of line has a negative slope. So let's say that the slope of this line is -1. So let's consider this, and then let's say that the intercept is c is equal to 0. So you can find the intercept using this origin point. So we know that the coordinate of this particular point is 0 comma 0, right? If you take those values 0 comma 0 and substitute here, okay, so if we put y is equal to 0 and x is equal to 0, you will get your c is equal to 0, right? So your intercept value is 0 if your line starts like this. So let's say that we have a line which starts from this particular point and it is like this. So in that case, let's say that this coordinate, this point is 2. Okay, so let's say that this is 2. So in that case, this particular green line has an intercept of 2. So it is basically the intercept value is equal to y value when your x value is equal to 0. Okay, so you can remember that. So if you take this, if you substitute your x is equal to 0, in that case your intercept is equal to y. So we know that how we can find this intercept value, right? So similarly, for this green line the intercept value can be 2, but in this case for this blue color line the intercept value is 0 as this passes through the origin. Okay, so that's what you need to understand. So we have two data points, P1 and P2, minus 3 comma 0 and 3 comma 3, and then we have a hyperplane represented by this blue colored line, and the equation of this line is y is equal to mx plus c, where m is the slope of the line which has the slope of minus 1 and the intercept c is equal to 0. Now what I'm going to do is I'm going to take these two parameters. So this slope and intercept are the two parameters of my line, right? And I'm going to take these two parameters and I'm going to store it in a variable called as w. So let's call this w as the parameters of the line. You can think about this as the weight that we talk about in models. So we know that we have weights and bias in our models, right? So let's say that these two parameters m and c, the slope and intercept, is our weights, and you can represent this m as m comma c, which is minus 1 comma 0, right? Because we have given the value for slope as minus 1 and intercept as 0. So basically w will be a vector or an array with the values minus 1 comma 0. So now what we are going to do is, so I'm taking these 2 points, and now I'm going to take the transpose of this w. So the w is minus 1 comma 0. So I'm taking the transpose of this w and I'm multiplying it with x. So x is nothing but my point. So the point here is minus 3 comma 0, right? And now I'm just multiplying this. So this is just like a simple matrix multiplication. And the reason I'm taking transpose of w is that we know that the shape will mismatch for matrix multiplication. If you want to carry out a matrix multiplication, the number of columns in the first matrix should be equal to the number of rows in the second matrix, right? So if you look at this, the shape of this matrix is 2 comma 1. So 2 rows and 1 column, and the shape of this matrix is 1 comma 2. So 1 row and 2 column. So the column of the first matrix should be equal to the number of rows in the second matrix, and that is the reason we are taking this transpose. If you don't take this transpose, you cannot multiply this, right? So that's the reason we are taking the transpose of this w. So we are taking the transpose of this w vector, and then we are multiplying it with x, and if you do that you will get the value of w transpose into x as 3, right? So we can say that for all the points which lie in this space in the left side of this blue color line will have a positive value. Now let's consider this P2 point. If you take this point, and similarly if you try to take the transpose of this w and multiply with x, and in this case the x is this P2 3 comma 3. If you multiply this it will be minus 1 into 3, which will be minus 3, and 0 into 3 is 0. So you will get w transpose into x as minus 3, which is a negative value. So the main inference that you can infer from here is, for all the points which lie in the left side of this hyperplane, w transpose into x value will be a positive value, okay, as you can see here. Whereas for all the points which lie in the right side of this blue colored hyperplane, w transpose into x value will be negative. So this is how our support vector machine classifier will try to classify the data points. So it will try to multiply the data point with the parameters of the line. So w basically is the parameters of the line, which is m and c, parameters of this blue color line. Okay, so it will try to multiply this data point value, which is minus 3 comma 0. So data point or coordinate value with the parameters of this line, and if you get the value as positive, and it can say that it lies in this space, and if the value, the product of this w transpose transpose of w and x is negative, it can say that that data point lies in this space. Okay, so you can try this for different data points. You can just take some data point here. So let's say that this data point here is minus 2 comma 0, or else you can take a data point here like minus 2 comma 1, any data points which comes under this space. So all the for all the data points you will get the w transpose x value as positive values, and all the values in this side which comes in this space will be negative. Okay, so this is how it will try to classify our data points. If the value is positive, then it will say that the data belongs to this group of data. If the value is negative, it will belong to this group of data. Okay, so this is how it will try to classify our data points. Now we need to understand few more things. So in this case, this w transpose x will act as our label. So if the label is positive, then this is a red color data point. If the label is negative, then it will be this green color data points, right? But this hyperplane won't pass through the origin all the time. So in some cases, so let's say that we have this green color data points and red color data points, and this hyperplane, it exactly passes through this origin. and in some cases that won't be the case. So let's say that we have data points. You can see here that the data points have been shifted towards the right. So you can just compare these two data points, and we have the hyperplane here, and this hyperplane does not pass through the origin, and there is some distance between this coordinate axis and this line, and this will be your b value, which is called as your bias. So if your hyperplane passes through that origin, you can say that your label will be w transpose into x, and this value will be positive or negative for one group of data and for the another group of data. And in some cases, if you have a bias value, you will have the label value as w transpose x plus b, where b is your bias value and this will be your label. Okay, so this is what you need to understand, and in most of the cases we will be having both weight and bias for our model. So this is what you need to understand. So this is how the equation of this particular straight line looks like: w transpose x plus b, which is similar to y is equal to mx plus c format, right? So it is similar to it. And one more thing, so it's not that if a point lies in the left side, it will be positive, and if it lies on the right side, it will be negative. So that is not a general case. If you see that we have a hyperplane in this direction, right? So if the hyperplane is in this direction, you will get all the points, so all the values as positive for left side points and all the values for right side point. But in case, let's say that we have a hyperplane that is in this direction. So if you have a hyperplane in this direction, it will be just inverted. So all the data points which lie in this side will get a positive value, and all the data points which lie in this point will get a negative value. So it is just vice versa. So I'll just remove this. So one thing you need to understand is, if it is in this direction, yeah, then in that case, so for all the data points in the left side, the value of w transpose x will be positive, and for all the data points which lie in the right side, the w transpose x value will be negative. If the hyperplane is in this direction, if it is in the opposite direction, then it will be the opposite case. Okay, so that's what you need to remember. And in most of the cases, the hyperplane may not pass through the origin, and in that case, the label will be w transpose x plus b. So this is another thing you need to understand. Now, so we know that we have these two kind of data, so red colored circles and blue colored circles, and we are going to draw a hyperplane, right? But we can draw different hyperplane in this space. So this can be one hyperplane, and this black color line is another hyperplane, and this orange color line is also another hyperplane, right? So all these data points can classify these data points, or they can separate these two data points, but we need to understand which is the best hyperplane, right? So that is our important goal. So in machine learning, this is how we deal with. There can be multiple solutions, but we need to figure out which is your best model. So what is the best parameters for our model, right? So we need to figure out that. So that will be our next step. So we are going to figure out which is the best hyperplane. So this is where the margin and support vectors comes into play. As I've told you before, for a support vector machine model, this margin space should be maximum so that it can make good prediction. So it can have a good cushion value, right? So we will try to maximize this margin value up to a certain extent. So we cannot keep on increasing this margin value, but this margin value should be maximum, for making good predictions, right? So now we are going to understand how we can increase this margin value. So let's discuss that, and we can call this as the optimization part. So we are optimizing our support vector machine model in order to get better parameters value or better hyperplane. So as I've told you before, there can be any number of hyperplane, but we need to choose the best one. So that's what we are going to do now, and we know that in order to have the best hyperplane, the margin space should be high. So let's discuss that. So let's say that we have two groups of data, green color data points and red color data points, and I'm having a hyperplane which is represented by this w transpose x plus b. So we know that if we have both weight and bias value, we can represent the label as w transpose x plus b, where this label can either be positive or negative, right? So if this label is positive, we can say that that data point lies in this group. If the this particular value w transpose x plus b is negative, we can say that it belongs to this green color data point, right? So now I'm going to draw this margin lines. So we know that we have already discussed what is meant by support vectors. So support vectors are the data points which lie closer to the hyperplane. So if you look at this data point, this green color point and this red color point lie closer to this blue color line, and hence we can call these data points as a support vector, and we can draw a line on them. So if you measure this distance, Okay, so just a second. If you measure this distance will be your margin space or margin distance. Okay, so let's say that this particular line, the coordinates of this particular line is represented by x1, and the coordinates of this line is represented by x2. Okay, and if you try to find this x1 minus x2 value, that will be your margin distance. And once we find this margin distance, we will try to increase this value, this margin distance value. And we know that the equation of this hyperplane is w transpose x plus b, which is will be our label. So this label is nothing but either a positive value or a negative value. So it can be anything. It can be -1, -5, -6, so on, or it can be +1, +5, +6, or so on. So we are not interested in the magnitude, but we are just interested in whether that value is a positive value or negative value, because this is just a classification task, right? So we just need to find whether it is positive or negative. And we know the equation of this blue color line is this, and let's say that the equation of this red color line is given by this red colored equation, which is w transpose x1 plus b is equal to 1, and w transpose x2 plus b is equal to -1. Okay, so we know that for all these data points, if we multiply the w transpose with the x1, so x1 is nothing but the coordinates of the points present in this side plus the bias value, you will get positive values. So let's for simplification purpose, I'm taking the value as 1, but this is not the case. So this value can be 1, 2, 3, or so on. But the only main thing that we can tell us it will be a positive value, right? Whereas for this data points, when you take w transpose and multiply it with x2 and add it with bias value, you will get a negative value, right? So let this negative value be 1. So let's just take simple values for simple calculation purposes. So this is how the equation of these two line looks like, because we know that for all the data points on this side we will get a positive value, for all the data points you will get a negative value. So basically what we are doing is, so I'll just go to my previous slide where we try to do that. So as you know that we have tried to multiply this w transpose with the x value, right? So x is nothing but your coordinate. So in this case, what we are basically doing is we are trying to project this point onto this blue color line. So this is just like a projection of vectors. So in our mathematics module, we have discussed about projection of vectors. This is simply that we are just trying to project this red color data point in this line, and we are trying to find it. So that's what is mentioned by this product w transpose into x. Okay, and that's what we are doing here. So the only difference is that we have some bias value. Okay, so this is the w transpose x1 plus b is equal to 1, w transpose x2 plus b is equal to -1, and this x1 minus x2 is your margin distance. So how you can find this margin distance is, if you have two lines, so let's say that we have two lines, this green color line and red color line, and we want to find the distance between them. So how you can find the distance between them is, you can subtract these two equations. So if you subtract these two equations, you will get the distance between them. So it's just math, basic algebra. So we every one of us have studied this in our high school, right? So we will try to do some elimination process where we will try to find the value of the variable. So I'm just taking these two equations. These two equations are the equation of the line, green line and the red line, and I'm trying to separate this equation from this equation. Okay, so this is your red colored equation, and this is your green colored equation, which corresponds to the green colored line and the red color line. So I'm just subtracting this. So this w transpose x2 will take a negative value, this b will also take a negative value, and this -1, so this minus and this minus will be get multiplied, it will be a positive, right? So what happens is, I'll just mention this here. So there will be a negative value here, and negative value here as well, and this negative will be turned to a positive, right? Because we are just multiplying it with negative value. Now if you do that, so you will get the equation like this. So w transpose x1 minus x2, this b and b will get cancelled because we have plus b and minus b, so we are just basically subtracting the equation. So you will get a 0, so this b and this b will get cancelled, and 1 plus 1 is 2, so you will get w transpose x1 minus x2 is equal to 2. And we know that this x1 minus x2 is the margin distance, and this is what we are interested in. So we need to remove this w transpose t. So we cannot simply take this to this side, so we cannot do that. So this is not a numerical value, but this is just like a vector. So in that case, what we will do is we will take the norm of w. Okay, so you can see here, so we need to divide the equation on both the sides by norm of w. So this is like magnitude of a vector. So if you consider this w as your vector, we want to divide it by the magnitude of the vector, and in that case this w transpose will cancel with each other. So that's the case. So let's write this like this. So we are dividing both left hand side and the right hand side with this norm of w, and in that case what happens is this w transpose and also this w norm will get cancelled, and the final equation you will have is x1 minus x2 is equal to 2 divided by norm of w, so which is nothing but the magnitude of w. Okay, so this will be your margin distance. So this is very important for us, so you need to remember this. So we have the x1 and x2 value, x1 minus x2, which is our margin distance, and this margin distance is given by 2 divided by norm of w, and our goal is to maximize this margin value. Okay, so now let's see how we can maximize this margin value. So that's what we are trying to do here. So we are trying to optimize a support vector machine model so that it can have a maximum margin value. Okay, so we have seen previously, right? So this label can have either positive value or negative value, right? So we can simplify this and write this like this. So yi, so yi, let yi be the label of each data points. Okay, so this yi, the label will be -1 if this w transpose into x1 plus b is less than -1. Okay, so if it is a negative value, so this basically means everything is a negative value. If negative value, this yi will take the label value as -1. If the value is greater than 1, so if this particular value is greater than 1, then we will take this as +1. So this is just like label encoding, because like for some data points the value will be -1, so for some data point it can be -5, -10, and so on. So what we just need to simplify this, and we are just creating two labels as -1 and +1. So if the label is less than or equal to -1, which basically means if the value, this w transpose x1 plus b value is negative, then we need to give the y1 yi value as -1 if the w transpose x1 plus b value is greater than or equal to 1. So this basically means that if the value is greater than 1, we need to give the yi value as 1. So we have two labels. So if the yi value is 1, then it comes under this data points, and if the yi value is -1, we can group them in this data point. So this is just simplifying the labels for our data points. Okay, and now we know that we have the margin. So x1 minus x2 is equal to 2 divided by norm of w. So our goal here is to have this maximum margin, right? So we can write this as, we should have the maximum value for 2 divided by norm of w, which is our margin, such that my yi should be -1 when this particular value is less than -1, and my yi, which is the label value, should be +1 if my value is greater than 1. So this is the important thing that we need to remember. Okay, so I'll just put this in a bracket. So this is very important for us. Okay, so you can just take a note of this if you want. Okay, so we are just trying to maximize this margin value such that my support vector machine model makes good predictions, where the prediction is if the w transpose into x1 plus b value is negative, I want the label value should be -1. If the w transpose x1 plus b value is greater than 1, then I want my label value to be +1. Okay, so this is what we can do. And now we are just going to rewrite this particular equation. So we are just going to rewrite this in a better sense. Okay, so maximum margin without overfitting. So just forget this statement. Let's try to understand what we have here. So this is the margin value we have, right? So we have explained this two equations. So I want a maximum value such that I get labels like this. So maximum value of 2 divided by norm of w. So the other way of writing this is minimum value of norm of w divided by 2. So instead of saying I want to maximize the label, I want to maximize the value of 2 divided by norm of w, what I can say is I want to minimize the value of w divided by 2. Okay, so I'm just taking the reciprocal of this part. So instead of saying this, you can say that I want to minimize this value, because we know that it's not easy to maximize some value when we are doing or when we are training a machine learning model. So if you remember in our previous logistic regression, linear regression models, we will try to minimize our loss function value, right? So similarly we will try to minimize this value, and if this value is minimum, then that means this value is maximum. What is this value? This is nothing but our margin. So the basic idea is to increase this margin. So increase this margin space. So how we can do this? Either by increasing this value, or we can decrease this value. So we are minimizing this value. Okay, so that is what represented here. And Now you can see this new term here. So C into summation of epsilon I. So what this basically means is C is the number of errors and epsilon I is the error magnitude. So we know that our goal is to maximize this margin value, right? But we cannot keep on increasing this margin value. As I have told you before, if you remember, I have already mentioned you that we cannot keep on increasing this margin value. So there should be a limit, because if you keep on increasing, then your model might overfit. So we don't want overfitting problem, right? So when overfitting occurs, all the training data points will be classified properly, but your test data points won't be classified properly, because your model won't get a general idea. It will try to overtrain from the data set. So we don't want it. So what happens when you overfit is, if you have the data points in this cases, let's say that we have red color data points and the green color data points, and one red colored point lies closer to this green color data point, and one green color data point lies closer to this red color data point. So these two are like outliers in our data set, right? So if you don't include this error part, then your model cannot find this error. So it will try to overlook them. It will try to overfit to the data point. So we don't want that. So in that case, what we will do is include this error part. So what I'm basically doing is I am allowing the model to make some errors, to make some mistakes. So this C is the number of errors that my model can make, and this ei or epsilon I value is the error magnitude. So error magnitude is nothing but what is the distance between this red colored line, this margin line, and this red colored data point, and what is the distance between this green colored data point and this particular line. So these are errors, right? So our model cannot classify these data points correctly, but that is fine, because if you try to overtrain your model, then that's not something that we want, because it can make a lot of mistakes in our test data. So we will let our model to make some mistakes, so that it cannot make overfitting problems. So we will try to minimize this norm of w by 2 value. Along with, we will give some tolerance for error, which is represented as C into summation of epsilon I, which is the total error magnitude, where C is the number of errors and epsilon I is the error magnitude for each data points. Okay, so this is how you can maximize your margin without overfitting. So this is how your support vector machine classifier will work. So it will try to find this margin. So it will try to find this hyperplane, and it will try to maximize this margin. So instead of writing this maximizing 2 by norm of w, we can say that we want to minimize this norm of w divided by 2, and I'm allowing it to have some errors so that it doesn't overfit. Okay, so this is how a support vector machine model works. So it will try to multiply the w transpose with the particular coordinate, and it will try to find whether that value is positive or negative. So this is how the equation looks like. So w transpose x1 plus b, if it is a negative number, it will take the value as -1. If it is a positive number, then it will take the value as +1. So this is how a labeling basically works in a support vector machine classifier. And I hope everyone is thorough with this particular part. And if you have any doubts, please mention in the comments. Okay, so that's it from my side, and I'll see you in the next upload. Thanks for watching.